Hello. In this video, we start the content of chapter of week 4, the chapter corresponding to diagonalization, and the first topic, which is just the basic notions of eigenvalues and eigenvectors. Since you have in the lessons section in Polyformat all the contents, my advice is that while you are listening or watching this video, you are just studying the contents in lessons. So use both things at the same time. This is a good idea. But well, I will try to go straight to the point and save some time and some details. So if you need more complete details, you just can go to the lessons where everything is explained. And of course, if you have any doubts, you can contact me. So let us start from the beginning, which is the definition of a notion. The first thing we are going to define is what is an eigenvalue. So for us during this whole week, we are going to work with a square matrix. So if it's a matrix A, which is a square, this means that it has the same number of rows and columns, in this case n, whichever n it is. And let us fix a real number. We could keep this definition for complex numbers, and this will lead us to diagonalization in the complex numbers. But we are just going to concentrate to focus on real numbers, just because we prefer to understand this properly, and we understand that you are more comfortable with reals than with complex numbers. So, given a real number, we say that lambda is an, I will change the color, eigen value of A if, and this is the key part, there exists a vector u in Rn, which is not zero. This is minus 0, so it's just saying that the vector u is not zero, such that, and this is the important idea, if I multiply the vector u by the matrix A, what I obtain is simply the vector u, but multiplied by lambda. So somehow the vector u remains the same, but multiplied by this constant. In this case, even though this is explained later in the lesson part, this vector u has also a name. In this case, u is called an eigenvector of A associated to the matrix A and to the scalar lambda. So, okay, this is the definition, the basic definition. This means basically that we have a notion for numbers, which is eigenvalue, and a notion for vector, which is eigenvector, and they are both connected by a formula. The formula that connects both notions, eigenvector and eigenvalue, is this. This and these are the eigenvectors, and this is the eigenvalue. And observe that the matrix plays a very important role. Okay, so once we know this definition, we need some more information. So the first thing we know is that we can construct the following. First, sigma of A is going to be the set of the lambdas in R, such that lambda is eigenvalue of A. So this is just, let us pick all the eigenvalues of the matrix A and put all of them inside a bag. In this case, the mathematical bags are sets, so in this set. This set has an important name and a very fashionable name, which is spectrum. And this is the spectrum of the matrix A. This is a fancy way of calling the set of eigenvalues. So sometimes instead of asking about computing eigenvalues, we can ask to compute the spectrum of a matrix. Given a number in the spectrum, so given a number which is an eigenvalue, I can pick all the eigenvectors. So we can define the set E sub A of lambda, which is the set of vectors U in Rn, such that AU equals lambda U. So this is the eigenvectors of A associated to lambda, and also the zero. The zero, by definition, is not an eigenvector because if we multiply the matrix A by zero, the result is always going to be zero. So zero is always an eigenvector of any number. So it has no sense. So we just simply eliminate the zero as eigenvector. But we need to add this vector, the zero, to this set. This set also has an important name, which is called the eigenspace associated to lambda. So again, going deeper in the idea, given a matrix, I can find some eigenvalues, and these eigenvalues form what is called as the spectrum. Okay. Now fix one of these eigenvalues, lambda, and find all the eigenvectors associated to lambda. Well, all these eigenvectors, we put them in a bag, in a set, and we obtain this eigenspace. Why I'm calling this set eigenspace and not eigenset? The reason is because this set is always a linear subspace of Rn. You have studied this in the previous week, but if the notion of linear subspace is not clear for you, I will simply recall a quick thing, which is what happens in R2, for instance, or in R3. In R3, the subspaces are first the trivial one, which is the zero. Second, the lines such that the zero through zero, and three, the whole the planes through zero, and finally the whole R3. So let's complete this box. The whole R3. Okay, so these are the subspaces. So basically, a subspace is of R3 or R4 or R2. It's the same. It's always the zero, the lines that goes through zero, the planes that goes through zero, and so on. Depending on if they are lines or planes, we can find a basis that describe the vectors. So the vectors describing a lines are just with only one. So a basis for a line is one vector, and a basis for a plane consists of two vectors. So we need two vectors for describing a plane. This is explained in the contents of the third week, last week. So you can review the topic of linear subspaces. And again, if you have any doubts, you can make any question to Santi, to me, or whoever. Okay, so since this is a linear subspace, we can hope to find bases. And the whole thing of diagonalization will be finding bases for these subspaces. Okay, so once this is clear, I was just to tell you the last maybe crucial thing in this first day topic, which is how to compute the eigen values. So in order to compute the eigenvalues, we have the following property, which is in fact a theorem, but okay, property, that says that lambda is an eigenvalue, so lambda belongs to the spectrum, if and only if the determinant of the matrix minus lambda times identity equals 0. This is equivalent. As soon as we are able to find one eigenvector, we have this. And this determinant is therefore given a name, which is called the characteristical polynomial of the matrix. So this also has a name, characteristic polynomial of the matrix. So if we write this in terms of polynomials, the equivalence is that a number is an eigenvalue if and only if lambda is a root of the polynomial. So once this is written, we can say simply that the spectrum is just the root of PA of lambda. When we describe the roots of a polynomial, the spectrum, we need to say which are the roots, and also we need to speak about the multiplicity. This is well explained in lessons, but in this case, in order to explain this in a theoretical approach, what I will do is in the next video that you can find, you will see an example, because these things are much better understood by examples. So we will pick a matrix and we will try to compute the spectrum, and I will tell them what is the multiplicity and how it is computed. So this is everything for this video.